In order to help us create force net equations and calculate the net force, free body diagrams are needed. A free body diagram consists of the following: the types of forces acting on the object, the direction of the forces, and the relative magnitude, represented by the length of the vector, or you could also write it in. If the net force acting on an object is 0, the object is not moving at all, or is moving at a constant velocity. So it's the velocity staying the same, no more force is being exerted on it, it's just cruising. If the net force acting on an object is not equal to 0, the object is accelerating or decelerating. Okay, now just a little review of the forces that we did at the beginning of the course. So the first one, force of gravity. We said this is Fg, little g. Normal force is Fn, the force that is always exerted perpendicular to a surface. The force applied, which is F-app, or F-A-P-P, small. This is the force exerted by any machine, animal, human, etc. Any force that's being actually exerted on the object. The next one is the force of friction, which is big F, little f. This is the force that opposes the direction of the motion of an object due to the two surfaces rubbing up against each other. And that could just be, air friction, right? The air rubbing up against, say, an insect's wings, or it could be, the ice, or it could be friction on this table, okay? Next is force of tension, which is F and then T, either big T, big T. This is exerted by a rope or an object at the point where the rope is attached to the object. So it's tension from a rope or a cable or a string, anything like that that's causing tension. Okay, so how do we draw a free body diagram? Well, here are your directions. So you can use, basically it's a flow chart, so you can use the whole page to make a flow chart. So this is kind of overall what it will look like, so you can write big-ish if you like to. I know some of you don't write big anyways, but anyways, okay. So first, identify the object for the free body diagram. So figure out what's moving or not moving. The next thing you do is sketch the object in isolation. So assume at the beginning that it's by itself, and then put with a dot in the center. Now, if it's saying a baby is crawling across the room, you don't have to sketch a baby for 5 minutes, just draw a box as the baby, okay? So it doesn't matter. You could draw a baby for 5 minutes if you like drawing babies, but that might be a waste of your time in physics class. Okay, next is identify all forces acting on the object. Next, choose appropriate reference coordinates and include which directions are positive. So similar to our kinematics unit, we generally assume that things like up, forward, right, north, and east, these are all positive things. Down, backward, left, south, and west. These are all negative things. There's still one more arrow, I ran out of room. So then the last thing is that you draw forces proportionally extending out from the dot at the center of the object. So let's do an example. So a child is crawling across the carpet to the right. So first, kind of to make sure I'm drawing everything right, I actually am going to say this is the direction of motion. Sometimes that helps just to remember and set up your free body diagrams appropriately. So like I said, I'm not going to spend a long time drawing a baby, so I'm just going to draw a box. And you put a circle, or a dot, in the middle. Now, since the child is crawling, they are applying a force in the direction of the right. So I'm going to draw, here's an arrow going out from the middle, and this is F at, because it's going in the direction of the motion. This is the way that the baby is pushing the direction. Opposing that is FF, the force of friction. Now I'm going to draw the force of friction a little bit smaller because I know that the child is crawling, so the FF must have to be bigger than FF. It must overcome the force of friction, so it needs to be a smaller arrow. Then always there's the force of gravity acting down. So there's FG acting down. And then perpendicular to the surface is always FN. And it's basically opposing gravity. But these are going to be the same. try and it doesn't really matter that they're exactly the same, but these are going to be the same because is the child either floating up or falling down? No, so these must be the same because they are staying on the surface of the ground, right? So Fn and Fg we assume that they're equal. Okay, now I think about, they're going to the right, so my F must be positive. So I think about F being positive. F must then be negative because it's the force pulling it to the left, and I know that that left means negative. Fn is positive and Fg is negative. So when we look at these as both an x and y vector, I can say all of my x is equal to Fnet is equal to F plus Ff. These two things added together will give me the total F, or the net F, of the child going horizontally. Okay? My y is Fnet is equal to Fn plus Fg. If these are the same, what will it end up being? 0. If F is bigger than Ff, then it will end up being a positive number, right? Because we know they need to go forward. Okay.
So why are you writing those down with the x and the y?
Because I'm looking at this is my horizontal information, this is my vertical information. We have to look at the Fnets separately because things are happening horizontally and things are happening vertically. I have to break them down into those vectors. Just like when I did in the first unit, I always broke stuff down into x and y when both are happening at the same time.
So how do you know that, why wouldn't it be F plus Ff? Like why is it Ff plus Ff?
Oh, it could be the other way around.
Okay.
Yeah, it could be Ff plus Ff. It doesn't matter. But the one thing that does matter is that you know these, right? If that you know that you set your Ff to negative, right? Because that will really impact your answer. Okay, let's do the other one. A toy rolling across a carpet after a child has pushed it. And what direction is it going? Oh, it doesn't say. Let's just say
It's west.
Oh, west? Okay. So, the direction of motion is now going west. So, direction of motion. You can draw a car or you can just draw a box and put a circle in the middle. Is there an F app? Is a force being applied at this moment in time when I'm looking at the toy car? No, it's after the child has pushed it. So there is no longer an F app being applied. So I'm going to make a note to that. No F app because no longer being pushed. It's after it was pushed. So I just don't even draw it in because it doesn't exist in this situation. But FF is going to be pulling it the opposite direction, in east. I don't know exactly the magnitude, I just draw it in, guess. And then I have, again, my Fn, and my Fg should be about the same because, again, the child is not falling or being pulled up by anything. So, in this situation, x is Fnet. What is my x? Only horizontal. It's only FF. I don't add FF because there is no FF for this one. And y is Fnet is equal, again, to Fn plus Fg. Okay, so that's the theory part of it. The math questions, this is when it gets fun, okay? So put your socks on.